In chapter 1, we looked at first order linear differential equations, so now we turn our attention to higher order linear differential equations, and we start in section 2.1 with second order linear differential equations. And recall that the order of a differential equation is the order of the highest derivative that appears in it. And also we say that it's linear. This is a formal definition. If the function and its derivatives are only powers of 1 and they have coefficients that are at worst functions of x. So now we define a second order linear differential equation. This is just simply saying that we have a function of x and the function y that we're looking for, its first derivative and its second derivative, set equal to 0, let's say. And g is linear in the dependent variable y and its derivatives. So in general, this is the way we would write a second order: some function of x times y double prime plus some function of xy prime and some function of xy equaling some function of x. So here's some examples. So this is linear because all of the derivatives are of powers 1, and there's it's a second order because the highest order derivative is 2. So that's a linear second order differential equation. This also is linear second order. Notice how the first one had coefficients of the function and its derivatives that are constants. Here we've got coefficients that are functions of x, but that's fine. It's still linear. And again, it's second order because that's the highest derivative. And these two examples in number 3 are nonlinear. First one's nonlinear because we have a derivative that's being raised to a power, so it's not a power of 1. And the second one is nonlinear. So this is nonlinear. And the second one is nonlinear because of the part of the definition that said they have coefficients that are at worst functions of x. So here we have, if you consider either y or y prime as the primary factor in the term, its coefficient is not just a function of x. So therefore, it's nonlinear. So, as I've mentioned before, we're only going to be studying linear, and we focus our attention on second order in this section. And we further define the second order, which is, here's our standard form again. If the function f of x is 0, then we say it's homogeneous. Some people pronounce that homogeneous. I say homogeneous. If it's not 0, it's non-homogeneous or non-homogeneous. So you want to definitely be able to identify a homogeneous and the difference between a homogeneous and a non-homogeneous, and it's obviously very easy. So here's an example of non-homogeneous because it's a function of x that it's equal to. It's second order and non-homogeneous, but any non-homogeneous has what we call an associated homogeneous, where we take the left-hand side in standard form and set it equal to 0 to force it to be a homogeneous. So it's what we call, again, the associated homogeneous. So in general, this is a form for the associated homogeneous differential equation to the given non-homogeneous differential equation. And we noted here that in physical applications, that function typically corresponds to some external force. We'll see some applications later where this function might be an electromotive force in a circuit, and could be a constant, it could be a variable, but we'll see those situations arise. So we start with what we call the principle of superposition. And if you have two solutions, call them y1 and y2, to a homogeneous linear equation, second order, here, which we actually rewrote to fit the form where the coefficient of y double prime is 1. So we basically just divided everything in our homogeneous equation here by a of x. So then we ended up with a new function p of x and a new function q of x that are the coefficients of y prime and y respectively. And that again was to make the coefficient of the y double prime equal to 1. So if those are two solutions, and we often see this in mathematics on the interval I, and if C1, C2 are constants, then any linear combination is also a solution. So C1y1 plus C2y2 would also be a solution. And that's what I noted here, is that any linear combinations, see we have a sum or difference here, and constant multiples, C1 and C2 of these two solutions, y1 and y2, we're saying that that will also be a solution. And then we have the existence and uniqueness theorem, and you could read through the formalities of the theorem, but basically it's saying, it's just guaranteeing that there's a particular solution based on initial conditions. So the first theorem is very important about the linear combination, and the second theorem is just saying that there's a particular solution, a unique particular solution for the given initial conditions. So in the examples, we're asked to use those theorems to first verify that y1 and y2 are solutions, and then use the principle of superposition to form a general solution that's a linear combination of those two solutions, and then find the particular solution based on the initial conditions. So, to be formal, we'll say for y sub 1 equaling, okay, we'll do the e to the 3x. Okay, we're going to need two derivatives, so y sub 1 prime to verify. It's going to be e to the 3x times 3, or 3e to the 3x, and y sub 1 double prime will be 3e to the 3x times 3 again, so 9e to the 3x. Alright, so to verify, we're going to substitute. If you want, recopy the equation. Note that it's homogeneous, second order, linear, y double prime, 9e to the 3x, minus 9 times y, which is e to the 3x. And pretty much by inspection we see that's true. We'll put a little question mark on the initial substitution, but you can obviously see that 0 equals 0, so it checks. Alright, so we'll leave you to check y2. So that's done in a similar way. Alright, so now we know by the principle of superposition or I'll just say superposition. Or you know what, let's just say that this means that y equals C1y1 plus C2y2 is also a solution. So that means that y equaling C1 times y1, which is e to the 3x, and then plus C2 times y2, which is e to the negative 3x, is also a solution. And we just want to find the particular solution. So to find the particular solution, we're going to use the two initial conditions, and note that the initial conditions are just the function and its first derivative. So we'll just need one derivative here, y prime. And the derivative of c1 e to the 3x is going to be c1 e to the 3x times 3, or 3c1 e to the 3x. And similarly, the derivative of c2 e to the negative 3x is going to be c2 e to the negative 3x times negative 3. So negative 3 c2 e to the 3x. Alright, so now for the particular solution, we use the initial conditions. And the first initial condition was that y of 0 is negative 1. So then that gives us negative 1 equals, okay, so we're substituting into y here. So negative 1 would be c1 e to the 0, so just c1. And then plus c2 e to the 0, or just c2. So note that that's one equation with two unknowns. And so our second initial condition, y prime of 0, was given to be negative 15. And substituting into our first derivative here, we would have that negative 15 equals 3c1 minus 3c2. Because when x is 0, these e to the zeros. Oops, made a mistake here. This should be a second term should be e to the negative 3x. Didn't have an effect though. Okay, so therefore we have to solve the system. Actually, let me move it over here. Okay, so the system is that negative 1 equals c1 plus c2, and negative 15 equals 3c1 minus 3c2. Now you can solve the system of two equations and two unknowns any way you like. If you use matrices, you know, you're in linear algebra and you know how to use matrices, Gaussian elimination, you could use Cramer's rule. I'm just going to do it the old-fashioned algebraic way. And what I notice here is that I could actually take this bottom equation and divide it by 3. What I'm going to do is what's referred to as the addition method, trying to make the coefficients of one of the variables equal but opposite. So I'll recopy the negative 1 equaling c1 plus c2, and if I divide everything by 3 here, I get negative 5 equals c1 minus c2, and now the coefficients of c2 are equal but opposite, so I can add them together, and I get negative 6, and that eliminates c2, so we get negative 6 equals 2c1, and c1 would be negative 3. And so whenever you're solving a system and you solve for one of the coefficients, Then to solve for the other, you just simply back substitute. And I apologize here, I did make a mistake. I copied down the addition as negative 15. It was positive 15, so I want to fix that, and I apologize. So that becomes positive 15, these positive 15s, positive 5, and that changes this to a positive 4. And C1 is 2. Okay, so again, I apologize for that. So it was just a copying mistake. And as I was saying, whenever you are solving a system of two equations and two unknowns, if you solve for the first one of the constants, then you just back substitute to solve for the other. And you could either use either one of the originals or either one of the modified equations. I'm going to use the negative 1 equals C1 plus C2, and C1 we found was 2, so negative 1 equals 2 plus C2, and C2 would be negative 3. Okay, so then that gives us our particular solution. Y is C1, 2, e to the 3x, plus C2, and negative 3, e to the negative 3x. And again, that's our particular solution. Okay, so another example. So that one involved E. Here's an example with some trig functions. So first, the verification. So we'll say for y1, which is given to be cosine of 5x, we'll need two derivatives to verify. So y1 prime would be derivative cosine minus sine, same argument 5x, derivative of the argument 5, so minus 5 sine of 5x. Second derivative, sine goes to positive cosine, another factor of 5 makes it negative 25. Cosine of 5x. So for the verification, we substitute. If you want to recopy the original equation, or if you just want to show the substitution immediately, either way is fine. But we get negative 25 cosine 5x, and then plus 25 times y was cosine 5x. Is that equal to 0? And yes, it's obvious. 0 equals 0, so it's verified. And then for y2, which is sine of 5x, I'll leave you to do that and check. So very similar routine. Okay, but now by the principle of superposition, so this is the important part, because checking is just kind of busy work sometimes. But the important part here is to use the principle of superposition to form a general solution, which is of the form C1 y1 plus C2 y2. And we're going to replace y1 and y2, obviously. So we have that y is C1 cosine 5x plus C2 sine of 5x. And to use these initial conditions again, we're just going to need one derivative. So y prime, and derivative of cosine minus sine, same argument 5x, derivative of the argument 5, so we get minus 5 C1 sine of 5x, and then we have plus c2, derivative sine, cosine, same argument 5x, derivative of the argument 5, so plus 5c2, sine of 5x. And now we'll find the particular solution based on the initial conditions. So the first initial condition that was y of 0 is 10. So let me make sure I copy that down correctly. Again, I apologize for the earlier mistake. And one thing about sines and cosines, when we make this substitution, I'm going to show it literally into the function y. We have 10 is equal to c1 cosine of 0, because 5 times 0 obviously 0, and then plus c2 sine of 0. And you could use your calculator or think of the unit circle or think of the graphs of the trig functions. But one thing that you always want to make sure you memorize, this is what makes trig functions easier when you're dealing with initial conditions, is that the sine of 0 is 0 and the cosine of 0 is 1. Okay, so that's very important. And that's what makes evaluating things that involve these trigonometric functions a little bit easier, because one of them at the initial condition of 0, sine or sine in particular, is always going to go to 0, because the sine of 0 is 0. And the cosine of 0 is 1, so therefore we immediately get that 10 is C1. Okay, and then we use the second initial condition, that y prime of 0 was negative 10, and that gives us, substituting in y prime here, negative 10 equals minus 5. Okay, I'm going to show it one more time, but in the future, we're not going to show the substitution of 0. But we get minus 5c1 sine of 0 plus 5c2 cosine of 0. But again, sine of 0 is 0, cosine of 0 is 1. So here we get that negative 10 equals 5c2, and c2 is negative 2. Okay, so then our particular solution, now that we found the constants, is that y is equal to c1, which was 10, cosine of 5x plus c2, which is negative 2, times the sine of 5x. And that's, once again, our particular solution. Okay, so got a couple more examples to go over. And in the first one, well, number 3 that is, we now have a situation where y1 is just an exponential function, but y2 is a product of an exponential function and an algebraic factor, in this case x. So I'm going to show the verification for y2, because y1's easy, right? So for y2 equaling x e to the 5x, we have that y2 prime is first times the derivative of the second, so that's x times the derivative of e to the 5x, which is e to the 5x times 5, so 5x e to the 5x, and then plus the second factor, e to the 5x, times the derivative of the first, and the derivative of x is just simply 1. So here's a situation where if I want to find the second derivative, it might be advantageous to factor out e to the 5x. You don't have to, but I'm going to choose to do so. And now for my second derivative, y sub 2 double prime. We've got the product rule again. First factor e to the 5x, derivative of the second, and the derivative of 5x is 1, or excuse me, is 5. Derivative of 1, of course, is 0. So that's 5e to the 5x. Then plus the second factor, and that's 5x plus 1 times the derivative of the first, and the derivative of e to the 5x, 5e to the 5x. So times the 5x plus 1. And then, if we want, let's simplify that. So y sub 2 double prime, 5e to the 5x, plus 25x e to the 5x, plus 5e to the 5x, gives us 10e to the 5x, plus 25x e to the 5x. Alright, so now the verification, we'll substitute. We've got the equation y double prime minus 10y prime plus 25y is 0. So that's going to be 10e to the 5x plus 25x e to the 5x, and then minus 10 times. Let's use the unfactored form here of 5x e to the 5x plus e to the 5x, and then plus 25 times y, which was x e to the 5x. That has to equal 0. And so, just separating this so we don't get confused. Take the time to show this. 10e to the 5x plus 25x e to the 5x. Oh, I should put a little question mark above the equals, right? Distributing the negative 10, negative 50, x e to the 5x minus 10 e to the 5x, and then we've got the 25 plus 25x e to the 5x, and that's equal to 0, and again we don't know yet, but now it's obvious because the 10e to the 5x's go away, and this 25 and this 25 make up 50, x e to the 5x, which cancels with that, negative 50, and 0 equals 0, so it's verified. Alright, so now the main part, principle of superposition. Y is C1, Y1 plus C2, Y2. So that gives us C1, Y1 was, and again you could check Y1 on your own, that's an easy one to check. C1, Y1 is e to the 5x, and then plus C2 and Y2 x e to the 5x. Okay, but once again, when we use the principle of superposition and we want to find a particular solution based on the initial conditions, it's always going to be just the first derivative that we need to calculate, if it is second order. So we only need y1 prime here, and the first term, c1 e to the 5x, differentiates to be 5c1 e to the 5x. Okay, I'm going to do this kind of carefully here. We'll do the c2, and then we'll have the product rule on this one. So first times the derivative of second, that'd be x times 5e to the 5x, or 5e to the 5x, and then plus the second e to the 5x times the derivative of the first, which is 1, So just plus e to the 5x. And I'll just leave it at that, and we'll go to the initial conditions. So first initial condition, y of 0 is 3. So going to y, we have that 3 is equal to c1, and then if x is 0, actually let me just put it over to the right here, 3 is c1 and that's all there is to it, because we're substituting into y is 0 when x is, or excuse me, y is 3, so that's how we get the 3 equaling, then c1, x is 0, so e to the 0 is 1, but this x causes the c2 term to go to 0. So that unfolded immediately. And so then the second initial condition was that y prime of 0 is 13. So that gives us 13 is equal to, and then if x is 0, here we get 5c1, and then plus, if x is 0, this term goes away, and we just get e to the 0 times c2, or plus c2. And so we can now, there's an equation with two unknowns, but we already know c1, so 13 equals 5 times c1, which is 3, plus c2, that's 15, subtract it, we get negative 2 is c2. So then our particular solution is y equaling c1 is 3, e to the 5x, plus c2, which is a negative 2, x e to the 5x. Okay, I think I'm going to stop there for this video, and we'll come back and do a part 2, because there's still a few more concepts besides this example number 4 that's going to be a little bit tedious with regards to the algebra. So we'll stop there, and we'll see you for part 2 of section 2.1 when you're ready.